So how does this connect to 3D printing? Well, uh, what I find fascinating is that 3D printing unlocks geometry. So it allows us to make new kinds of geometric structures, and geometry unlocks performance. So we can really do new things with geometry that we couldn't do before. So we can borrow ideas from mathematics and we can leverage mathematics in the material world. So maybe more concretely, the kind of question you'd be asking here is, I'm starting with some data. I have a target performance, I have manufacturing constraints, and I have some physics. And I want to know what shape will answer, be the answer to that question. What shape will meet those targets and satisfy those constraints and be okay with that physics? So I'm going to show a couple examples from our customers. This one is interesting because again, this is kind of going the other direction. It's taking an idea from mathematics and it's making it material in the real world. And 3D printing is that unlocking mechanism. So these triply periodic minimal surfaces that probably you've seen in your work in 3D printing, these were first described in the 1800s. And what's interesting is that they were described as mathematical structures only. So the very first publications on these didn't even have any pictures, which is why I've kind of grayed this one out. So Schwartz was the first person to identify these. This is one of his well-known structures, but it's only recently, it's only with 3D printing that we've been able to actually manufacture these structures. This is something I find so exciting. Later in the 70s, we have the gyroid, and now we have people like Salia, who is a Swiss-based startup, who are using these structures to do things like make cell scaffolds for lab-grown meat.